Hello again. Right, now let's move on to chapter 2.3 on lateral earth pressure. Okay, so examples of what we mean by lateral pressure. You probably have seen this before, commonly enough, in the low wall. And when you start to have the nursery above the wall, will be overgrown with the vegetation. In simplified form, you see that the pressure that's acting on the wall, the sideways, is increasing, and the wall will start to give way. Right? And if we represent that in the model box, model test setup, as you can see here, this is the wall, this is the soil, and this is a pressure diagram that's been sketched out with a marker pen outside the box on the perspex. So PA is active pressure, B is a triangular form of the pressure. So just very quickly now, you can see that if this is a pressure diagram and is triangular in shape, it tells us what? At a ground surface, where there's zero soil on the surface, zero soil mass on the surface, so you get the zero pressure there. But as the depth increases, the pressure will increase due to the soil weight itself. So whatever that's on top at this point, say, will be translated into a horizontal force, and it goes down and down. That's why it gets bigger as it goes to greater depth. An example of lateral earth pressure failure. This was a picture taken on a railway embankment in Kobe earthquake 1995, which was quite a major destruction in Japan. So what happened here is that during an earthquake, the dynamic force of the earthquake will densify the soil, the backfill behind this wall, and the wall couldn't take the extra dynamic load, and also the soil that is being densified hence become of a greater force pushing the wall, hence it collapsed. Another example, this was the Niigata earthquake 2004, highway embankment slipping away because of the retaining wall giving way. Yeah, right, this could be partially considered as a slope failure as well. Right? Okay, when we talk about lateral earth pressure analysis, we can't run away from two big names here. One is Rankine and the other is Coulomb. Let's go through what Rankine tells us first. As per Rankine's theory, when we try to analyze an earth pressure, lateral pressure acting behind a wall, just look at a simple diagram like this. This is the wall, and this is the soil that you are trying to retain at the back. If you are not trying to retain any soil behind the wall, there's no point of erecting the wall in the first place, right? And in the soil, usually we'll have a groundwater table, as you can see here in the inverted triangle. And this first diagram, the red triangle, is to show us the water pressure. So we know that the water pressure is the same at any point, and it just increases with depth. And that is why when you're in a swimming pool and you move from shallow waters to deep waters, you find that the pressure you feel on top of your head is getting greater because of the water mass over it exerting the pressure on you. So similarly here, the deeper it gets, the hydrostatic pressure will become greater. Next, the second diagram, we are looking at the force that is being exerted by the soil itself. So of course the soil starts from the ground surface, goes right down to the base of the wall. Again, the soil mass that is coming down the depth, the greater the depth, the more soil you have above that point, alright? Hence there will be a greater force that is acting on the wall. And similarly, on the other side, if you like, of the spectrum, we have the passive pressure. And if pushing towards the soil, pushing towards the wall is called active pressure. Then if it's moving away, it is called the passive pressure. Do not get too worried about this. It's just a situation where the way we describe the forces. So in simple terms, if a soil is strong, the greater the strength, the greater the passive pressure, and the lower the active pressure. We'll see later on why. Okay, just take note now before we move on to the next slide. When you're talking about the water pressure behind the wall, you do not multiply by any factor. You see, there's no K or whatsoever. But when we're talking about active or passive pressure, there's a Ka and Kp going on here, right? Okay. Whenever we talk about lateral earth pressure in a clay soil, just clay, not sand, there is a possibility of something called the tension crack taking place. A tension crack is simply something that happens near the ground surface, probably goes down to like no more than 5 meters deep. And the depth can be calculated by a simple formula of Z equals to 2C over gamma. Gamma is the unit weight of the soil, and C is the cohesion of the soil. You don't see any phi around, right? Meaning that this is a pure clay. And this is a part, this is a diagram where you can see that it is on the left side of the center line of the wall. That means it's in negative form. This is zero earth pressure, meaning what? The soil is pulling back into itself, hence you can see a crack between the wall and the soil. When there is no contact, if there's a crack, that means there's no contact between the soil and the wall. Is there any more earth pressure acting on that part of the wall? There's this part? No. And that's why this bit of things is considered negative, and you minus off from the total earth pressure that's acting on the wall. So in this particular diagram, the earth pressure is actually the purple line, the purple triangle here. Okay? And for tension crack, because there's no lateral pressure acting on the wall, it has been estimated that you could actually make a cut without any support right up to 3.85 C over gamma. That is, if you are same on supports, you don't want to put any support, and you want to cut the soil, you can go up to that depth without putting any support, because to that depth, there is no pressure, no lateral pressure acting on the wall anyway. So theoretically, the wall won't be being pushed forward or pushed down into the excavated site. Right? However, Rankin's theory has got some limitations, and they are only valid for situations like this. Number one, the back of the wall is smooth. But think about it, most of the walls we're talking about are made of concrete material. Is concrete really that smooth? Not exactly, right? Number two, the back of the wall is vertical. So, for simple example, yes, we like to assume that the wall is vertical at the back, but they are not usually that case. We'll see later on as well. Number three, the sand behind the wall is horizontal. Wall, soil at the back view. Not necessarily is horizontal, right? It could be slanting. It depends on the situation. Like you see along the highways, most of the time, the wall is actually retaining a slope. Number four, the wall is long in comparison with the height, so it's a two-dimensional situation. So this is probably valid. This is most of the cases, because the wall is long. And finally, there's enough displacement to tilt the wall to generate active and passive states. So this is alright. Now let's take a look at Coulomb's theory. Now, Coulomb's idea, the first thing is that it says the soil, when you're talking about lateral earth pressure, it is not just about the soil being pushed outwards horizontally. Right? In the active case, look at the blue arrow, is towards the wall. Passive case is moving away from the wall. There is also a component that is coming down. It only makes sense, right? If your soil is being pushed outwards, surely the tilting will cause the soil to be going downwards as well, as indicated by the pink arrow here. In the passive case, obviously, you will see as if the soil is moving upwards because of the tilting of the soil mass. Right? So this is what Coulomb has told us. And in order to analyze the lateral earth pressure, Coulomb's idea is to form a force polygon. Right? As you can see here, there are four forces. Right? Four forces acting here. One, the soil weight itself. You can see this W, the soil weight at the back of the wall. And because of the soil weight, you can see that there's a normal force acting here due to the shear resistance along this plane, and there is a cohesion resistance acting along parallel to the failure plane. And at the front of the wall, you see that there is a reaction force. So these are the four forces that can be that need to be resolved using the a graphical method or the Coulomb's method. Okay, this diagram, this table is in your module. You can look at it for the details, which are the known and which are the unknowns that we need to identify from using Coulomb's method. Okay, now very quickly we'll go through the factors that can affect our lateral earth pressure. Number one, the displacement of soil. We talk about active, passive. Active means the soil is moving towards the wall. Passive means it's moving away from the wall, pulling towards itself. There's a third one, or rather it's actually the first one, which is the situation where the soil is at rest. It's not moving anywhere, not moving forward and not moving backwards. So that is at rest. Okay, and the second factor is the strength of the soil. Generally, if your soil is of high strength, then it will exert less force onto your wall. Why? Because if your soil is strong, then it can hold itself in a stable condition. There's no need for it to want to lean onto the wall. Make sense? Hence, if it is stronger soil, then will have less active pressure or passive pressure acting on the wall. Number three is the water table. Remember, with the first diagram we talked about, in referring to Rankine's theory, the hydrostatic pressure. When you have water in the soil, it's going to exert additional force onto your wall, but it depends on where the groundwater table is. You do not simply take the hydrostatic pressure to be starting from the ground surface, because if the groundwater is below the ground surface, you've got to omit the part that is from the ground surface right up to the beginning of your groundwater table. Alright? And the second effect of having groundwater table is that it will reduce the effective stress. Remember, when you want to calculate effective stress, you take the total stress minus off the water pressure. Why? Because water in the soil, number one, is fluctuating all the time. It can be seasonal, it can be due to rainy season, it can be due to all sorts of factors. And secondly, water will cause buoyancy in the soil. So that is not helpful in terms of effective stresses, the actual stress, actual strength that you have in the soil. Number 4, sloping soil surface. The larger the inclination, the wall, the larger the inclination of the soil that is behind it, then the greater the force that's acting on. Right? When you resolve this horizontal force, this inclined force into the horizontal and vertical component in the vector case, you could see that it will increase your horizontal pressure on the wall. Number 5, Number 5 is your wall friction. So we did agree that in Rankine's theory, says that the back of the wall is actually smooth, but in Coulomb's case, we got to take into consideration the fact that it is not smooth. There's a friction. So imagine if the back of the wall is rough and there's a soil, the backfill at the back, right, that is pushing towards it. This friction will actually help to engage the soil and the wall. So this will actually be helping in reducing the lateral pressure because it adds on a vertical component. I repeat, the friction between the soil and the back of the wall actually adds on to a vertical downward component. And when it's going downwards, it's actually reducing your lateral earth pressure. Right? So it increases the wall stability consequentially. Number 6, wall inclination. If you have a wall that is not straight at the back but inclined, you see that will have an effect on the wall as well. Why? Because when it's inclined, it's this way, the soil that is above it is actually sitting on it and adding on to the self-weight of the wall. So that will actually add on to the stability of the wall as well. And now you understand why most of the walls that we see out there, especially the gravity walls, are not built with a straight vertical back. And last but not least, we are talking about the surcharge load. If at the back of the wall, you have the soil backfill, and you put loads on it, building something, a car park, a building, whatsoever, this surcharge load is going to add on to the horizontal pressure acting on the wall. Alright, the details of these 7 factors are in your module. Please go through them. Okie dokie, now let's look at the soft examples. We'll just pause for a bit.